This is a video key to the Stoich Strikes Back assignment. This assignment has two parts. The first part includes a type of problems which is known as leader-to-leader problems, which are actually pretty easy. And then the second half of the worksheet is mixed stoichiometry problems. The mixed stoichiometry problems are actually quite a bit challenging. They're going from any quantity of substance, meaning any amount of liters or grams or moles or particles of one substance, to any quantity of another substance. And so you really have to have a mastery of this entire chart that we have here to be able to do those mixed stoichiometry problems. At the beginning, though, we're doing something that's actually relatively easy. We're going from the volume of one substance to the volume of another substance. And so if you notice here, we're going to start here, and we're going to go here to volume, and that's really just a one-step problem, and we can use for that conversion factor, we use that mole ratio. And the reason we can do this is because the mole ratio indicates a proportionality in the balanced chemical equation. That proportionality exists between particles, which include things like molecules and atoms, and it also includes things like moles. However, because at STP, 1 mole of a gas occupies 22.4 liters, volume is also proportional according to the mole ratio. And so these volume-to-volume conversions are actually very easy. They're just one-step conversions. We're still using the coefficients from the balanced chemical equation to try and make a conversion there. And that's how the first half of this worksheet will be. And as I said, it's pretty simple. And so first, starting looking at this, we need to balance the chemical equation in each of these. So that is 3 and this is 2. If you're struggling with balancing, I encourage you to look back at my earlier video on balancing chemical equations, because I won't really be reviewing that here. So this one, it starts with 4.0 liters of ammonia, 4.0 liters of NH3. On this one, you might not know what ammonia is right off the bat, but hopefully you identify that nitrogen is N2 and hydrogen is H2, and then ammonia is the only thing that's left in there. So that would be a good way of identifying what ammonia is, even if you don't know the formula there. It's in the chemical reaction. So then we're trying to get to volume of nitrogen. So looking at the coefficients, if we're trying to get from liters of NH3 to liters of N2, we look at the coefficients that they have here. There's a 2 in front of NH3. There's a 1 in front of N2 in that balanced chemical equation. So we use the coefficients just like we would if we were doing a mole-to-mole conversion, and that's how this works. All right, so if we have 4.0 times 1 divided by 2, 2 sig figs in our answer, so we need it to be 2.0 liters of N2. These all go about the same. It said in regard to that same reaction, what volume of ammonia is produced if from 9 liters of hydrogen. So we start here at 9.00 liters of H2. All right, and again, we're just going to be doing a liter-to-liter conversion. So that's from liters of H2 to liters of NH3. And we know that there are 2 liters of NH3 for every 3 liters of H2 based on that balanced chemical equation. Again, we're just looking at the coefficients there. And if we do that, we get 6.00 liters of NH3. The reason for the 6.00 instead of calling it just 6 is because we have to keep the sig figs right. And so we had 3 sig figs originally. The mole ratio is an infinite number of sig figs because it's a perfect ratio, and so we keep our 3 sig figs in the answer. For number 3 here, again, first thing we got to do is balance it. So I start by balancing the carbons. There's 3. Then I balance the hydrogens. All right, there are 8 on both sides. Then I balance the oxygens. If we count the oxygens from the CO2 and the water, there are 10 on the product side, so we put a 5 in front of the O2 to get that to balance. All right, we're starting here with 250 liters of propane. That 250 point means that that last 0 is significant, so 250 point liters of propane, which is C3H8. Again, on this one, you might not know the formula for propane, but you should be able to recognize everything else in that chemical reaction. And so by process of elimination, you know that propane is C3H8. So then we're going to go from liters of propane and we have to get into liters of CO2 because that's what I was asking about in this one. So we get to liters of CO2. We look at the balanced chemical equation. We see that for every 1 liter of propane, we end up producing 3 liters of CO2. Right? And we get 750, and then we have to have that point on the end again to maintain that 3 significant figures that we had, and it's liters of CO2. On problem number 4 here, there's that overbar or overline on top of the 4,000. That indicates that those first 2 zeros are significant, but the last 0 is not significant. So we have 3 significant figures in this problem. We're going to go ahead and balance the chemical equation. Get a 2 here and a 2 here. And then it says we've got 4,000 liters of water. So 4,000 liters of water is what we're starting with. And it asks us how much oxygen is produced. So what we know here then is for every 2 liters of water, that we're going to make 1 liter of oxygen. We get 2,000 as our answer. We want to maintain 3 sig figs here, so we put an overbar again over those first 2 zeros to indicate that the first 2 zeros are significant and then the last 0 is not, so that we have 3 sig figs in our answer. For problem number 5, it says what volume of carbon monoxide is consumed if 72.0 liters of carbon dioxide are produced, and how many liters of oxygen are necessary? So this is one of those problems where I ask you 2 questions in one, so we'll approach them each in turn. First, we'll do what volume of carbon monoxide is consumed. All right, so we start with 72.0 liters of carbon dioxide. And looking at the balanced chemical equation here, we've got to balance it. I know that there are 2 liters of carbon dioxide for every 2 liters of carbon monoxide. And those cancel out directly. You just get 72.0 liters of CO right out of that. So it's the same thing that we started with because it's a perfect 2-to-2 ratio. And then for the oxygen here on this one, we're going to start again with the same thing, 72.0 liters of CO2. All right, and we still have 2 liters of CO2 in the bottom, but we're trying to get into oxygen this time. So we know that there's 1 liter of oxygen for every 2 liters of CO2 based on that balanced chemical equation. And so this ends up being 36.0 liters of O2 is your answer there. So that is the end of the part of this worksheet that is on the liter-to-liter conversions. But as I said, they're pretty straightforward, they're pretty easy. In addition to those, a type of reaction that is similar is the particle-to-particle conversion. Again, we're just using the mole ratio. It works exactly the same. It's a one-step conversion. So particles to particles, moles to moles, and volume to volume, those are all pretty nice, simple one-step conversions if you need to do them. All right, now I'm going to jump to the back section of this, which is on mixed stoichiometry problems where we're going from any units of one thing to any units or any quantity of another thing. And the first one on the back here has us starting with 50.0 grams of KClO3, and it's asking us how many molecules of O2 are produced. So we're going from grams of KClO3 to molecules of O2. So going back here to map out this problem, the substance we're starting with is KClO3. All right, we're trying to go to molecules of O2. So where we're starting here is grams, so we start with mass, and where we're trying to end up with is molecules, which is particles of O2. And so this one, there are a couple of different paths that you can take, but unless you're going directly particles to particles or directly volume to volume, I would ignore the top and bottom paths on that mole ratio. So what we're going to do is we're going to go from moles, from mass to moles for KClO3. All right, and then we're going to go from moles of KClO3 to moles of O2, and then once we're in moles of O2, we can get to particles. And all the conversion factors are listed out there. We need to know the molar mass of KClO3. We need to find the mole ratio, which will be found through using the balanced chemical equation, and 6.02 times 10 to the 23rd particles in 1 mole. Those are the conversion factors that we're going to use. So keep that in mind as we set up this problem, because we'll go through exactly those steps. We start here. I'm going to get my conversion factors ready, so we need to have a balanced chemical equation so that we can use the mole ratio. So balancing this chemical equation, I get 2, 2, and 3 for the coefficients. We also need the molar mass of KClO3. All right, so if you find that, you should get it's 122.55 grams. All right, and so what I'm going to do is I'm going to start off with this conversion. We start with what's given, 50.0 grams of KClO3. Then remember the first step. We have to go from grams of KClO3 to moles of KClO3. And that's using the molar mass. All right, then we're going to go from moles of KClO3 to moles of O2, because that's the other substance we want to talk about in this problem. And then we go from moles of O2 to molecules of O2. Writing in our conversion factors, grams to moles for KClO3, that's the molar mass. There are 122.55 grams in 1 mole. Mole to mole, we're looking at the mole ratio, which comes from the coefficients of the balanced chemical equation. KClO3 has a 2 in front of it. O2 has a 3 in front of it. Moles to molecules, that's the 6.02 times 10 to the 23rd. So 1 mole has 6.02 times 10 to the 23rd molecules. Now we have to look through and count our sig figs. All the ones that have moles associated with them in this case are all perfect numbers, so those are infinitely many sig figs. But 50.0 has 3, and 6.02 times 10 to the 23rd has 3. 122.55 has 5. So we go through the smaller number, and so we're going to end up with 3 sig figs in our answer. If you calculate that and round to the correct number of sig figs, you should get 3.68 times 10 to the 23rd molecules of O2. Number 7 says how many moles of KCl are produced in this problem number 6. So in this one, we're going to moles of KCl. We start off the same exact way, all right? We're going to have to go from the mass of KClO3 to the moles of KClO3, but then we want to end up in moles of KCl, all right, which is right here. So this is actually one last step, because we get here to moles and then we stop. So this is a 2-step conversion. We go from mass of KClO3 to moles of KClO3, and then we go from moles of KClO3 to moles of KCl. So we're going to start the same way, 50.0 grams of KClO3. And then we want to get out of grams of KClO3 and into moles of KClO3. And then we want to get from moles of KClO3 to moles of KCl. Conversion factor grams to moles is the molar mass. That's that 122.55. We already have that from the last problem. 122.55 grams of KCl in 1 mole. All right, then mole to mole, we're looking at the balanced chemical equation. Coefficients are 2 on both of these, so 2 and 2. Our answer should have 3 significant figures, and so you should get 0.408 moles of KCl. All right, number 8 says, what volume of NH3 is produced from 19.0 grams of H2 with excess N2 at STP? So in this one, we're going from grams of H2, and we're trying to find volume of NH3. So showing you this little flow chart for this one. We're starting here with H2, and we're starting with the mass, and we're trying to get to volume, which is liters for our NH3. The path I recommend you take here is go from mass of H2 to moles of H2, and then from moles of H2 to moles of NH3, and then from moles of NH3 to the volume of NH3. And so the conversion factors that we're going to need here, we need the molar mass of H2. The mole ratio comes from the balanced chemical equation in 22.4 liters in 1 mole at STP. So we're going to start here with balancing the chemical equation. We've got a 3 here, and we've got a 2 here. The next thing we need to do is find the molar mass of H2. It's just 2 times 1.01 from the periodic table, so that's 2.02 grams for molar mass of H2. Then we start with the number that's given in the problem, so 19.0 grams of H2. All right, then in this problem we are going from the grams of H2 and getting into moles of H2. Then we want to get rid of moles of H2 and get into moles of NH3. Then we want to cancel out moles of NH3 and get into liters of NH3 because it's asking for volume here. Writing in our conversion factors, there are 2.02 grams in 1 mole. All right, mole to mole conversion, we're looking at the balanced chemical equation. So there are 2 moles of NH3 for every 3 moles of H2. And then conversion factor liters to moles is 22.4 liters in 1 mole. In this case, we have 3 sig figs in our final answer. All right, if you multiply all those out and round, you should get 140. All right, but we need a point at the end to indicate that it's 3 sig figs and that that last 0 is a significant 0, and it's liters of NH3. For problems number 9, 10, and 11, I'm going to not look back at that flow chart because I want you to get in the habit of trying to see these problems without the flow chart because you won't be getting that flow chart on the exam. And so this one, it says how many moles of water are produced if 5.69 times 10 to the 24th formula units of sodium hydroxide are consumed according to the reactant below. So in this one, we're starting with formula units and we're getting to moles. We can go from formula units of sodium hydroxide to moles of sodium hydroxide and then from moles of sodium hydroxide to moles of water. All right, and so that's a 2-step conversion factor, 2-step conversion problem, I mean. And so we'll start here with 5.69 times 10 to the 24th times 10 to the 24th at formula units of sodium hydroxide, which is NaOH. All right, we need to get out of formula units of NaOH and get to moles of NaOH. All right, and then as the second step, we're going to get out of moles of NaOH and get into moles of water. Conversion factors, formula units to moles, that's Avogadro's number, that 6.02 times 10 to the 23rd. Formula units in 1 mole. All right, going from moles to moles, we need the balanced chemical equation. I forgot to balance it earlier, but I can do that now. All right, it's 2 and 2 there. All right, so actually this one ends up being 2 moles of water and 2 moles of NaOH because those are the coefficients on those in that balanced chemical equation. In this one, we end up having 3 significant figures, so you should get 9.45 moles of H2O. Because there were no gram to mole or mole to gram conversions in this problem, we didn't have to calculate a molar mass, which is kind of nice. For problem number 10, we're starting with liters of hydrogen, and it asks us how many atoms of zinc. All right, so In this one, again, we're going to go from liters to moles, and then from moles to moles, and then from moles to atoms. All right, and so we don't have to calculate a molar mass in this one because we don't ever go from grams to moles. We end up, to balance it, all you have to do is put a 2 here in front of the HCl. We're starting with 3.50 liters of hydrogen gas. We want to get out of liters of hydrogen and into moles of hydrogen. Okay, and then we want to get out of moles of hydrogen and into moles of zinc. And then we want to get out of moles of zinc and into atoms of zinc. Now filling in our conversion factors here, moles to liters, there are 22.4 liters in 1 mole. Moles of H2 to moles of zinc, that's the coefficients, so they both have coefficients of 1. And then moles of zinc to atoms, in 1 mole there's 6.02 times 10 to the 23rd atoms. This one has 3 significant figures as well. If you go through and multiply it out, you should get 9.41 times 10 to the 22nd atoms of zinc. And then for the last problem here, it says we've got liters of chlorine gas, and it says how many grams of aluminum chloride are consumed. And so this one, we're going to go from liters of chlorine to moles of chlorine, and then from moles of chlorine to moles of aluminum chloride, and then from moles of aluminum chloride to the mass of aluminum chloride. And because we're going moles to mass, we're going to need a molar mass for aluminum chloride. Also, we need to balance this chemical equation. If you do 2, 2, and 3, that should balance it out. And then, as I said, we need the molar mass of aluminum chloride, which is AlCl3. If you add up the masses from the periodic table, you should get 133.33 grams. All right, and then we start with the number that's given. That's 250 liters of Cl2. We want to go from liters of Cl2 to moles of Cl2. And then we're going to go from moles of Cl2 to moles of AlCl3. And then we go from moles of AlCl3 to grams of AlCl3. The mole to liter conversion, that's 22.4 liters in 1 mole. Mole to mole conversion, we're looking at the balanced chemical equation, so we look at the coefficients. Are there 2 moles of AlCl3 for every 3 moles of Cl2? And then gram to mole, we're using the molar mass from the periodic table. We calculated that as 133.33 grams in 1 mole. Right, we're going to end up having 2 sig figs in our answer because the original 250 here only had 2 sig figs. That last 0 is a trailing 0 without a decimal point. The other numbers here had 3 sig figs and 5 sig figs, so we go with the smallest number, which is 2, and our answer should have 2. So when you round it to 2 significant figures, you should get 990 grams of AlCl3. Right. This is a pretty complicated process. There's another set of homework problems called mixed stoichiometry problems. I recommend that you do that entire set of problems and check your answers with the PDF key that will be posted online. As I said, these are pretty complicated, so a lot of practice is necessary, and also it's important that you're checking that you get the correct answer with the correct sig figs and the correct units on every single problem, because that's how you will be graded when you take the quiz and the exam on this section.